f on the interval AB, then what should the integral from a to b of little f, what is that supposed, what should that represent, since little f is the velocity? The change in position. The change in position. In other words, big F of B minus big F of A. So, theorem, fundamental theorem of calculus part 2, arguably even cooler maybe, is that anytime you're computing the integral from A to B of some function, it is just big F of B minus big F of A, where F is any antiderivative, or F is any antiderivative of little f. Okay, before even taking a minute to talk about how awesome this is,
I like this one better.
let's just prove it. The proof is again pretty easy. Okay, so at least my proof is. So first of all, first I'm going to define an accumulator function. So let g of x be the integral from a to x of f. Okay. So let's just out of nowhere, let's just define this accumulator function. Well, by FTC part 1. Or by FTC, what I call it? By the real FTC. By the real FTC, I know that the derivative of g is f, right? Yeah. Okay, cool. All right. So now that's just a little thing off to the side. All right. Now I'm going to prove this. Let big F be any antiderivative. Any antiderivative of little f. Okay. Well, by the definition of antiderivative, what is the relationship then between big F and little f? I mean, this is not a hard question. If f is the antiderivative, what do we mean by that?
That means that f is the derivative of f.
Yeah, that means the derivative of big F is little f, right? Okay. So, but by FTC part 1, the derivative of this accumulator function is also little f. Okay? So, if the derivative of this accumulator function is little f, but the derivative of big F is also little f, what do we know about two functions with the same derivative?
They're the same. Except
Their shift.
Plus c.
Yes,
Yeah.
that is correct. So since the derivative of big F equals the derivative of g, big F and g must differ by a constant. By the theorem that we proved, right? So big F must look like g of x plus c. Okay, well, if that's true, then just compute f of b minus f of a. Do it. F of b? G of b plus c minus g of a plus c.
The C's cancel.
C's cancel. Yeah, so it's just g of b minus g of a. What is g of b?
That thing.
Integral from a to b of f. g of a. Answer?
Oh.
Which is just f of
Whoa. Whoa. Whoa.
So we just put, yeah.
Yeah. What this says is, this is like amazing,
Oh,
right?
yeah.
This is the most amazing thing in the entire world. Yeah. What this says is, take some function. Suppose you want to integrate some function, right? If you want to integrate some function, think about how much was involved in this process. We had to take this function. We had to partition up into subintervals. We had to evolve possibly of unequal widths. We picked sample points. We plugged them into the sample points. We multiplied by the widths. We took the atom up. We took the limit as n equals infinity. It turns out that this entire process is doable in just a single step if you should happen to know an antiderivative of this function. Whoa. That means, for example, the function on this quiz you took, which was the integral from 1 to 5 of 4x minus x squared.
Oh my god.
This entire process could have instead been accomplished, if you knew the fundamental theorem of calculus, by the difference in two antiderivatives. Do you happen to know an antiderivative of 4x minus x squared?
yes. 2x squared.
Yeah.
Minus
1/3 x.
1/3 x cubed.
Yeah, 1/3 x cubed.
Yeah.
Yeah, that seems to be an antiderivative on hand. That was a little more struggle than I thought it was going to be for you guys, but yes, that is an antiderivative of this. And therefore, if we call this function big F, it turns out that this entire integral can just be accomplished with f of 5 minus f of 1.
Oh my god.
And in fact, it is customary to compute
What?
this integral. That's right.
What?
Yeah, I knew you would be excited, Sydney. It turns out the notation that people use is they take the antiderivative evaluated at 5 and 1.
So cool.
So, what is this? What happens when I plug in 5? What do I get?
50
minus
like
125 over 3, is that right?
Yeah.
Minus, when I plug in 1, I get 2 minus 1/3. And so my answer is 48 minus 124 over 3, is that right? No, 126 over 3. Did I do that right? No, I did it wrong.
You're just adding a third.
I don't know. Minus
120.
plus a third, so that should be minus 124 thirds, right?
Yeah.
So what's 3 times 120 and 24? 144. 144 minus 124 over 3. Ta-da. Whoa. With the fundamental theorem of calculus, suddenly it becomes really, really easy to do integrals, assuming that you know an antiderivative. All right, and the bell's about to ring, so I'm just going to wrap up here. The fundamental theorem of calculus, I hope you enjoyed yourself today. What the fundamental theorem of calculus really says, it comes in 2 parts. Laura, it says that fundamentally differentiation and integration are inverse processes. The derivative of the integral of a function is the function, but also, if you think about it, I haven't written it this way yet, but the integral from a to b of the derivative of a function is the difference in the values of that function. This is actually the most succinct way to express the fundamental theorem of calculus part 2. That the integral of the derivative of something is the change in that thing. So on the one hand, the derivative of an integral is the function. On the other hand, the integral of the derivative of something is that thing too. Okay, guys, now all things are clear. And really, the rest of calculus is kind of just like a big letdown, right? Not really.
No, it's numerical methods.
All right, good. Blow all the things, eat all the food. symbol. Yes. That's why they have the same symbol.
Wait, what?
Alright, good. I'll see you guys later. Can you erase your board for me?